All right, so let's start today's lecture. So yesterday we have finished the first case where we do the selection on low cardinality attributes, and now let's look at another case where we consider the selection on high cardinality attributes. For example, if we consider, say, a specific city name in this example, then as you can imagine, if we this is actually a suburb name. So in Australia, there are thousands of suburbs. So it's not like those low cardinality attributes. We're seeking of different ways to handle this, and the solution would be a join index. So it's essentially the same as what we have introduced yesterday, where here the bitmap join index is essentially the combination of bitmap index and join index. Okay, so today we focus on join index, and hopefully I can give you a better intuitive and explanation for join index itself. So join index, as the name shows, it is an index, but it is a join. So what does this join mean, right? So let's look at index first. If you still remember, in traditional relational database, if we build an index, then we definitely build the index on top of a table, or say more specifically, usually we consider an index on top of a specific column or attribute. Okay. For example, if we're going to build an index on cities, let's say, okay, so the index would be on top of this location table, right? And the key are the cities where the say the value or the things you store is the location ID, because here we should have a location key, right? A location key and city. So city would be the key, and this the location key corresponds to each and every city, will be stored as a list, right, in the index. So it's something looks like this. So if we are using R tree, B tree, for example, okay, and for this key, we will store a list of location ID. Here is actually the transaction ID or the sales ID, which is the join means. So originally we should have a location ID, for example, location 101, location 203, or so on and so forth. So this is what we do for a traditional index. But for join index, this join means that what we store is not the location ID or the location key, it is the sales ID, okay, or transaction ID, as you can see here. Therefore, so join index relates the value of the dimensions, So these are the key of a star schema to rows in the factor table, right? So these are the rows of the factor table, and these are the values of dimensions the values of dimensions. So it should come from a dimension table, right? So for example, a join index on city maintains for each distinct city a list of row IDs, well, or transaction IDs of the tuples recording the sales in the city. So all these are R102 or R117, so on and so forth, they all have a location key which corresponds to an entry in this location table where the city equals to Kingsford in this example. All right. So that is why it's called a join index. So unlike the traditional index, what it stores is the row IDs of from the fact table, not in the original dimension table. And the join indexes can span multiple dimensions, or we can build a join index on multiple dimensions. Then, I mean, it will help us on different tasks. For example, let's say we have built a join index on location with key with city as key, right? And we build another another join index on customer with region as key. Okay, so for Kingsford we have say R102, R117, and so on and so forth, right? R20 maybe, just as an example. Okay, and for region, say for example, if the region is shouldn't be Australia, right? Yeah, probably we should build on type is better. Okay, if say we have built a join index using type in customer table as the key, and say the type is let's say the type is A. Okay, so for type A, we have built a join index, so it corresponds to a list of row IDs. Say this row IDs are R102, say R190, 200, and so on and so forth. Okay, so if we're going to say if, for example, we want to have the sales with customer type A and city Kingsford at any time, how we get the result? So we can simply join or merge these two lists together. Okay, because one of the list corresponds to the city equals to Kingsford. These are the row IDs, and another corresponds to the type of A. Okay, and if we do the merge, we will have say R102, R20, R200, and so on. Okay, but imagine if you don't have such kind of join index, you cannot do things so fast or so easily. All right, and this kind of join index span multiple dimensions. It can be implemented as a bitmap index. So it is a bitmap join index, which we have introduced before, or yeah. So you can use bit operations for multiple joins, but you can also just join the merge the two lists. Well, it really depends on the length of the list, as well as the length of the total transactions. Because for a bitmap join index, the length of the bit vector is equals to the length of the fact table, or how many rows in the fact table. All right, but since for join index, we're considering high cardinality attributes, so arguably we can expect that for each attribute value, the corresponding list won't be very long compared to those low cardinality attributes, right? therefore, if this list is not so long, then it might not be a good idea. It might not be a good idea to use use bit vectors. It might be better to just use the list, because the list would occupy less space. Okay. It's all about mathematics. I mean, you can make the assumption and do the calculation by yourself, and you would see the difference. All right. So this is the join index, and the next condition situation is to do arbitrary selections on dimensions. All right, so consider this scenario where we have selection conditions on different dimensions. For example, we want to select region equals to Asia for customer dimension, and we want to select a city which ends with Ford. Right? For example, Oxford or Kingsford in this location dimension. And for time dimension, we want to select those days that are school holidays. Okay. So the problem of such kind of query, say where we have selections on different dimensions, the traditional way of processing such kind of query is to use join, of course, in relational database, right? So we need to join these tables and then do the selection. Okay, this arguably is the most inefficient way. So a better way would be okay, we do the selection on each and every dimension tables, such that we can filter some of the data, right? And then we do the join using these 4 tables, okay, with their foreign keys and primary keys. So the problem of this is that the complexity of the join operation totally depends on the size of the 2 tables that are going to be joined together. And if basically for sales we have tens of millions or even more rows, right? It's quite a large number, and for those dimension tables, we may have a slightly smaller number of rows, but still it's a large number. And and all these conditions, these selection conditions, their filtering power or selectivity is not very high. So usually it's less than 10%. Let's assume. So this 10% is on. This 10% is on the sales. So for example, say if we use this condition with region equals to Asia, and if we join the sales table and the customer table together and apply this condition, we probably can just filter out say 10% of the total transactions, right? And similar things may happen for other conditions. Therefore, even we do the join in sequence plus applying the conditions here, it will not reduce the complexity of the join operation or the complexity of this whole query. All right. But if we consider all the conditions together, the selectivity is expected to be much higher. So that is the observation, right? Which means if we want to, so if we just want to find how many cells within the region Asia, we may have a lot of transactions. Okay, but if we consider the transactions within the region of Asia, happens in a school holiday, and the city is ended with Ford, right? Then we may have just a few or much fewer transactions compared to the total number of transactions. So that is the observation. Therefore, in order to do this, we proposed this star join idea. So basically, we do the join. So it's actually not a regular join; it's a cross join. If you know what it is. So essentially, it is the Cartesian product of these three tables, these three dimension tables. Okay, and also we only need to perform the cross join on part of the dimension tables, because we have those selection conditions, or say selection predicates here, right? So for example, we only need to consider a time which where the key is 1 and 2, because these are the only ones who is a public holiday. Okay, it is just an example, but just to show you the idea. So basically, the cross join, if we have, say, 2 entries for time, 2 entries for customer, and 2 entries for location, the cross join would be the Cartesian product of these 3 dimensions. So we will have in total 8 entries here. So it's actually 2 times 2 times 2. Okay, that's also why it's called cross join. Okay, so these are the if say these are just the keys. Okay, the primary keys of time, customer, and location dimension tables. Then these are the combination of foreign keys within the fact table that we need to select, or we need to maintain or keep. Okay, and if we apply this selection condition on the say on the fact table, it will be much faster. Well, we will see why later, but essentially you will quickly get the numbers or those rows that satisfies the condition. Okay, for example, here, because we have so this green rows are those that satisfy all 3 conditions. Okay, so this is what we do in a traditional way. Right, so we use sales, which is the fact table, perform the join with time, of course, under the condition of this selection, and then perform the join with customer, and then perform the join with location. But currently, we just do the cross join of these 3 tables with the selection predicates, and then we perform a join between sales and this new table. Okay. All right. So the next question would be why this is good, right? How does this reduce the time complexity? So there's one thing that you need to get straight before we continue. So that is, how do we implement a join operation within relational database? Okay. If you have taken the course of 9315 database implementation, then you probably know how to do it. But since this course is not in the prerequisite of this course, so I will briefly introduce the idea. So in general, the idea is that in relational database, especially when we consider traditional relational database, and we're actually using the external memory model, or say we count the IO cost, so input output cost. So input output cost is the cost that we need to transfer data from memory to disk, or from disk to memory. Okay, so from disk to memory is input, from memory to disk is output. Okay, so this is the I/O cost. So when we consider the I/O cost, and when we consider doing join, all right, the thing is, if we join two tables, so there are actually many different algorithms to perform join efficiently, based on the size of the tables. So in our scenario, we consider so in our example, or in our scenario, we consider the case is that, okay, this is the fact table, okay, and we know that fact table are quite large. So basically, for fact table, we're expecting to have millions or even tens of millions of tuples, right? But for the for those tables, either the time table or customer table or location table, or the cross join of these tables, especially after we apply the selection criteria, okay, we will have a very small table. Say at most, this is after we do the cross join, we would have like thousands of tuples. But you can imagine, I mean, before the cross join, we may have, say, tens of tuples on each table, and because the cross join, we would do the multiplication, right, between all this number of rows or number of tuples. So we will have thousands of them. So the thing is that in relational database, you cannot fit millions of tuples into the memory at one time. Okay, because the memory size is limited, and actually we consider the page size. So the page size is even smaller. So usually we consider, nowadays the page size is increased, but usually let's say we consider a page size of 4K bytes. Okay, so definitely for millions of tuples, it cannot be fit into one page. Okay, it has to be fit into several pages. However, for this for the thousands of tuples or even tens of tuples, it can be fit into one page, right? And when we consider the I/O cost, we actually consider say one load into so we load a table from say from the disk to the memory. It's one I/O. Okay, if we write back, it's another I/O. So the join is like we load this one, we load the small table into the memory, so it's one I/O, and then we need to do the join. So when do the join, we load. So assume there are several pages or several blocks. They're all basically the same concept in the fact table. So we load them each at one time, and we compare the tuples within this two pages. See the keys can match or not. Right? If it can match, then we keep it. Otherwise, we remove it. Okay, and after we done all we keep it somewhere in the memory, and after say we keep the tuples that we have kept so far is more than one page, we write it back. Okay, and each time we just read one page in and do this kind of join between two pages, and then we load the next page in. Okay, so let's say for the fact table, we have S pages. Okay, so it's 1 plus S per one join operation. Okay, so it's essentially the big O of S in our condition. Okay, it's all because we assume that the join between two tables, one table has S blocks or S pages, but the other one can be fit into one page or constant pages. Okay, so this is for one join, right? And if we consider the this scenario, which we perform the join sequentially, okay, then after this one join, because we have assumed that the selectivity of a single selection predicates is not very high. Okay, so it's around say 0.9s. This is the result after we join sales and time. All right, and then we perform the join again, so it would be another like big O of 0.9s, or you can remove 0.9 if you like. So essentially, you will do it again in our example. So you will get like you will get yeah, it's yeah, we probably should put 09081 before the big O. But essentially, it's about it's around 3 times the 3 times its big OS, right? But if we consider the scenario with star join, right? So we only have one join operation between sales or the fact table and the cross the result of the cross join between these 3 dimension tables. Right. So as we said, we assume this can be fit into one page or one block as well, or even several blocks. I mean, it is a constant number. So essentially, we will have a big OS as the time complexity of using star join. Okay, so you can see how using star join actually reduce the time complexity of this star query, right? So that is the idea, and that is why we want to apply this kind of star join. We want to do the cross join beforehand, right? It's all about to reduce the join operation between fact table and another table. And the assumption behind that, right? Because you usually don't see this in a traditional relational database. This is because we have some special condition or special scenario, which is usually the fact table is quite large, okay, have many rows. But for the dimension tables, they usually have a much less rows, right? So the overhead of the join is totally relies on the fact table. But so we need to somehow reduce the join involves fact table. So if we can do the join for the rest tables first, even it is a cross join. I mean, the problem of the cross join is actually enlarge the number of rows, okay? Because we need to list all the possible combinations here. It's not like a regular join. You actually shrink the number of rows. But with this, even with this cross join, I mean, as long as the result is still much less than much fewer than the fact table, right? We kind of achieve what we want. We reduce the number of joins that involves the fact table from 3 in our example to 1, and roughly we reduce the total cost by from 3 to 1 as well. Okay, so the new cost would be 1/3 of the original one. So that is the idea, right? Okay, so far we have we have considered the join operation and the selections. Okay, so all all the selections with the joins. So if we goes back to any example we have been discussed before, so this is a typical query language, right? So what we have is we need to do the join between tables, right? Like this part and this part. We need to do some selection, okay? But we also need to do a group by. Okay. So we have discussed the indexing and query strategies for say for join and for selection. Now we consider the techniques for for this kind of group by or aggregation. So we consider this coarse grain aggregations. So it's basically the high level aggregations. Right. So for example, we have assumed that the query is to find total sales per customer type in our stores in Europe. Okay. So if we use a join index, assume that we can prune 75% of the data, right? But we still have 1/4 of the total data. And considering the size of the fact table is quite large, this 1/4 is still large. Say it's several millions of transactions, right? And you can imagine if doing aggregation on top of even the remaining transactions, it would be expensive. Okay, by expensive means we need a long query response time because you need to go through each and every transactions and apply the aggregation function. And how do we reduce the response time here? So here the idea is actually related to the lattice of cuboids, or say the O column, or what we have introduced before. So for example, in this query, we have this query asked per customer type, give a specific location, but essentially you can do the aggregation over times, okay, over the time dimension. So basically, if we postpone this kind of aggregation after we get all the transactions, then it would be expensive. But if we have already done the aggregation on the dimension of time, so basically we have per customer type, per store region, but we have across all the times, okay? Then it can significantly reduce the computation time, right? So the idea is the pre-computation is necessary and is most beneficial. So basically, in SQL queries, it's called group by, but in data warehouse, it is essentially cuboids. Okay. So multi-dimensional aggregation is essentially equals to selection on corresponding cuboids. So for example, if we say we have 3 dimensions, time, customer, and location, and this is the original query where we do the join first, and then we group by type and city, right? So if say we for each dimension we first need to decide its level. So it's actually related to the query or related to the user's specification or the user's needs. But let's say we select some years, right? For the customer, we select some brands, and for location, we select some cities, right? So we first build a cuboid for year, type, and city, right? And then we do selection over these three conditions, right? So these three conditions, 1, 2, and 3, are to select specific years, brands, and cities, right? And then we do the group by. So here, what we can do to further speed up, or we can do to benefit from the cuboid, is that we can actually materialize some or even all of the cuboids. Okay, so materialize is like it's just like a materialized view in a relational database. Okay, it just gives you not only contains the original table, but also some result of a query. Or in our case, it's actually a summary using some aggregation functions. Okay. Let me see. So basically, it's something like. It's something like this. Okay. Something like the table here. Not the table here. We should have. Yes, it's something we have been doing here. Okay, so for the cuboids, we kind of extend it on different dimensions, right? We start from a 3D cuboid, and we generate the 2D cuboids, which are this, and 1D cuboids, and even the 0D cuboid. So this is essentially what we need to do, or what we want for this. So using cuboid to support such kind of queries. So there are two issues that we need to address. One is how to store the materialized cuboids, okay, and the other is how to compute the cuboids efficiently. So if you still remember the lattice of the cuboids, we're going to do something similar. Well, essentially the same. I mean, say we have 3 dimensions, A, B, and C. But in the rest of today's course, we actually A, B, and C refers to a specific level. Specific level of the corresponding dimensions. Okay, so this is our say 3D cuboid. Okay, and we can generate the 2D cuboid. Let's say BC, right? By do the aggregation on one dimension, right? And we can further generate 1D cuboids, right? So this should be A, B, and C. Okay. By do the aggregation on one dimension on the 2D cuboid, and then we can have the last 0D cuboid, where for every dimension it's actually all the data have been aggregated. So it's 3 all here. Okay. So first problem is how do we store this kind of materialized cuboids? Okay. So in relational OLAP, say this example is a 2D. Let me see. Yeah, it's a 2D table. So we have a product and a store. So this part is the original fact table. Okay. It corresponds to this part, right? Yeah, and for the rest part, like here and here, are the materialized result. Okay, so it's actually corresponds to we can divide them into these two parts, these three parts actually. Okay, so which means we have 4 group bys here. All right. If we group by store and product, this first part is what we have. So for each store and each product key, we would have a corresponding amount. If we do group by store, then for each store, we kind of do the computation over all the possible product keys, okay, and have the amount here. If we do group by product, we will have this part, right? So if we do group by nothing, we will have we will essentially aggregate everything. So it's here. So this is how we store a cuboid in Rollup or in Rollup. And this is the 2D case where you can think of the 3D case, which is essentially the same. Okay, you simply add another column, and well, I mean, the first part is still the original fact table. Or say if you do group by, if we add another column named time, then the first part should be grouped by store, product, and time, right? And then you group by store and product. You group by store and time. You group by product and time, right? And then you group by store, by product, by time, and then you group by nothing. Okay. So essentially, how many queries do you need to write in order to build such a cube within a Rollup? So the number of queries should be 2 to the power of d, which, if you remember, is exactly the number of cuboid within the cube. If we consider the lattice, if we consider the lattice of a cube, right? So because we have 2 here, so it's like we have store and product, then we have store and product, then we have all here. So we need 4 queries, which is 2 to the power of 2. And in the previous case, right, we actually have 8 cuboid here. Each one corresponds to a group by. So it's 2 to the power of 3. It's 8 queries. And for each and every query, we actually need to compute them independently. Okay, we need to compute them independently. This is a sorry, no, let me see. So if we consider the SQL queries for each and every query, it involves some join operation, which would be quite costly, and a group by. Okay, but how do we do it? I mean, efficiently, right? In Rollup. So below is the syntax in SQL if we do this kind of cube by operation, but the real, say, procedure behind this, there are two ways of doing this. So one is from top down, one is from bottom up. So we start from so top down is not a very good idea compared to the bottom up. So we will quickly go through it, and we will put more time to on introducing the bottom up approach to do to compute these cuboids. Okay, so for top down approach, so we first model the dependencies among the aggregates, which is quite straightforward if we have the lattice of the cube. right? So basically, say if, for example, if we have, of course, we have this, as this is the original fact table, right? So it's also the most detailed view, if you like. Then for this 2D cuboid, to any of the 2D cuboid, how do you get it? Because you actually keep product and store, and then do the aggregation on the quarter, right? On quarter. So it can be computed from view product store quarter by summing up all quarterly sales. All right. And similarly, you do the aggregation on product, you will get this one. You do the aggregation on store, you will get this one. Right. And for example, store depends on product store or store quarter. It doesn't matter which one you use. But you simply do the aggregation on store. You do the aggregation on product. You will get the view of score. If you do the aggregation on quarter from the store quarter cuboid, you will get the cuboid of store as well. Okay, and for the others as well. And for this one, actually you can choose either one of these three and do the aggregation. You will get the cuboid of this 0D cuboid. Okay. Again, let's use this 2D. So this one have 2 dimensions, A and B, where M is for measure. Okay. So as a top-down approach, this is what we have initially, and we will compute for each A the total sales, right? So for A we have 2 distinct values, 1 and 2, and then we consider all the possible B corresponds to A equals to 1. We will get the summation, which is 100 here, right? And similarly, we have 50 here for A equals to 2. And then we consider distinct B value, right, and do the aggregation on A. So we will have for B equals to 1, we have 2 transactions. So it's 50 here, and B equals to 2 is 30 and 20 and 50 again. Okay, so and these are the 1D cuboid, right? So we start from 2D cuboid. This is 1D cuboid. So how about 0D? We simply do, because 0D it's not on this slides, but essentially it is for A it is all, for B it is all, and for M you simply do the aggregation using either of these 2 tables. So it's 150. Okay. But note that when you do the thing is that when you do the computation of 0D cuboid, you don't start from the 2D cuboid. You start from 1D cuboid. Okay, that's the thing for a top-down approach. And we will have a break here, and we will then continue the bottom-up approach.